Next, we turn to material properties.
Here, I would like to introduce the column configuration and representative values of the valve material properties table for pressure-containing components. This table presents the minimum mechanical properties, showing tensile strength in both KSI and MPa units, yield strength also in KSI and MPa, followed by elongation in a 2 inches, 50 millimeters, gauge length, modulus of elasticity, and hardness. Looking at a representative row, the tensile strength is 70 to 95 KSI, 485 to 655 MPa, and the yield strength is 40 KSI, or 275 MPa. The modulus of elasticity is 27.9 times 10 to the power of 6 psi, which is 19.2 times 10 to the power of 4 MPa, and the Brinell hardness ranges from 137 to 187. Some rows contain representative values for individual materials, such as a tensile strength of 135 KSI, 930 MPa, and are marked with notations like Note 1 of Code 5. Next is the nickel-molybdenum alloy B2 bar stock, with specification ASTM B335 grade B2, UNS N10665, and an operating temperature of -325 to 800 degrees Fahrenheit, or -198 to 427 degrees Celsius. In terms of composition, molybdenum is the key element at 26 to 30%, while chromium is 1% or less, iron is 2% or less, carbon is 0.02% or less, and the remainder is nickel.
Now, I will introduce the cast nickel-molybdenum alloy B2, specification ASTM A494N7M. The operating temperature range is -325 to 1000 degrees Fahrenheit, which is -198 to 538 degrees Celsius. The most important alloying element is molybdenum, which makes up 30 to 33%, and the remainder is filled with nickel. Looking at the limited elements, chromium is 1% or less, iron is 3% or less, carbon is 0.07% or less, and silicon and manganese are each 1% or less. Impurities such as phosphorus are managed at 0.04% or less, and sulfur at 0.03% or less. This material is the casting equivalent of the B2 bar stock, specifically the B335 specification, and is used for valve components that exhibit excellent corrosion resistance in reducing or non-oxidizing acid environments due to its high molybdenum content.
This chunk defines the header for the modulus of elasticity column in the valve material properties table. It specifies that all the modulus of elasticity values listed in the table are measured based on 70 degrees Fahrenheit, or 21 degrees Celsius. The units are written as psi with MPa in parentheses, following a method of providing both imperial and SI units. For example, 27.9 times 10 to the power of 6 psi corresponds to 19.2 times 10 to the power of 4 MPa. You can understand that this header defines the measurement conditions for the modulus of elasticity listed in each material row.
Here, I would like to introduce the representative data for the Brinell hardness and reduction of area columns in the valve material properties table. The header consists of typical Brinell hardness and reduction of area percentage. Taking one row as an example, the hardness is listed as 42, 290 typical. The elongation-related value is 37 typical, and the reduction of area is 67 typical. Another row shows a hardness of 71, 490 typical, followed by 16 typical and 52 typical. In a high-strength row, the hardness is 115, 792 typical, 22 typical, and 63 typical, with a modulus of elasticity of 29.9 times 10 to the power of 6 psi, or 20.6 times 10 to the power of 4 MPa. Cells marked with 3 dashes in the table indicate that data for that item is unavailable. This section is a continuation page of the valve material properties table for pressure-containing components, and the material codes correspond exactly to the previous standard specification list numbers.
This chunk defines the headers for the strength-related columns in the valve material properties table. The header is titled Minimum Mechanical Properties, which is then divided into a tensile strength column and a yield strength column. Both strengths are written in KSI units with MPa units in parentheses, providing both imperial and SI units. This header serves to define which column and which units the tensile strength and yield strength data for each subsequent material row will be entered into.
Now, I will introduce the minimum mechanical properties table for valve materials used in pressure-containing components. This table pairs exactly with the material code numbers from the standard specification list discussed earlier, with each row representing one material. The column configuration includes tensile strength and yield strength expressed in KSI and MPa in parentheses, elongation in a 2 inches, 50 millimeters gauge length, modulus of elasticity at 70 degrees Fahrenheit, and either reduction of area or typical Brinell hardness. The modulus of elasticity is written in exponential form, such as 29.9 times 10 to the power of 6 psi, with the MPa conversion value in parentheses.
Let's look at the actual values in the table by category. Many stainless steel rows show a tensile strength of 70 to 95 KSI, which is 485 to 655 MPa, a yield strength of 40 KSI, or 275 MPa, and a modulus of elasticity of 29.9 times 10 to the power of 6 psi. High-strength rows show a tensile strength of 90 to 115 KSI, a yield strength of 415 MPa, and Brinell hardness ranging from 176 to 255. General austenitic steels have a tensile strength of 70 to 75 KSI and a yield strength in the range of 25 to 35 KSI. Precipitation hardening series, such as 17-4pH, reach a tensile strength of 125 KSI or 860 MPa and have very high hardness, exceeding 300. On the other hand, copper alloys and cast iron series have relatively low tensile strengths of 31 to 41 KSI and a modulus of elasticity of 13.4 times 10 to the power of 6 psi. According to the notes at the bottom of the table, the A216 Class B and Class C items are based on a 1.125 inches, 95 millimeters bar with a tensile strength of 34 KSI and a yield strength of 16 KSI.
This short chunk introduces the header that provides the reference conditions for the modulus of elasticity column in the mechanical properties table. The modulus of elasticity is measured based on 70 degrees Fahrenheit or 21 degrees Celsius, and is expressed in psi, with a converted MPa value provided in parentheses. These reference conditions apply commonly when interpreting all modulus of elasticity values in the properties table we saw earlier, and the same header is repeated whenever the table continues across multiple pages.
Now, I'd like to introduce the modulus of elasticity item within the material properties table for valve pressure-containing components. In this table, the modulus of elasticity is presented as a value at a specified reference temperature, which is 70 degrees Fahrenheit or 21 degrees Celsius. The units are provided in psi or pounds per square inch, along with the SI unit MPa or megapascals, so you can read and use them directly in both unit systems. The modulus of elasticity is an indicator of stiffness, showing how much a material deforms when subjected to stress within the elastic region. The larger the value, the smaller the deformation under the same load, meaning it behaves closer to a rigid body. In practice, it is used as a fundamental material constant when calculating the deformation and bending of pressure-containing components such as valve bodies or bonnets.
Next, I will introduce the continuing part of the material properties table for valve pressure-containing components. As indicated by continued in the table title, this is a large table that spans across pages. One of the items covered here is the reduction in area, which is expressed as a percentage and indicates how much the cross-section of the specimen decreased after the tensile test. A larger value means there is more room for plastic deformation before fracture, which is interpreted as superior ductility of the material. Another item is the typical Brinell hardness, which shows the hardness range of the material surface. Looking at the example values in the table, it is presented in the range of 156 to 207, allowing you to gauge the general Brinell hardness level of that material group. One thing to note is that the material codes used in this table correspond exactly to the codes in the standard specifications for valve materials list we organized previously. Therefore, by looking at both tables together, you can link the specifications and properties for each material.
Finally, I'd like to introduce the minimum mechanical properties item. This section defines the mechanical properties that a material must at least guarantee, with tensile strength and yield strength being the primary examples. First, tensile strength refers to the maximum stress a material can withstand before fracturing. Next, yield strength is the stress at which permanent deformation begins in the material, and it serves as the basis for determining allowable stress in design. Both strengths are listed in KSI, or kilopounds per square inch, along with the SI unit MPa, or megapascals. The important point here is that the figures in the table are minimum values. Therefore, the actual material is guaranteed to have strength equal to or greater than these values. Since these two properties are core data used directly when designing the thickness of valve pressure-containing components or determining pressure ratings, they are items you must check in the table.
Now, I will introduce the minimum mechanical properties table for control valve materials. This table summarizes the minimum strength, elongation, and modulus of elasticity guaranteed by the material for each material code. Continuing from the previous section. Looking at the main items of the table, it consists of tensile strength, yield strength, elongation, and modulus of elasticity. Here, elongation is the value representing the degree to which the specimen stretched until it broke, expressed as a percentage based on a gauge length of 2 inches. 50 millimeters. Strength values are written in KSI with megapascals in parentheses, and the modulus of elasticity is listed in psi with megapascals in parentheses.
Next, let's look at the core numerical ranges in the table. Tensile strength is widely distributed, from as low as 40 KSI, 275 MPa, to as high as 120 KSI, 760 MPa. Yield strength ranges between 18 KSI, 124 MPa, and 51 KSI, 350 MPa. And for the same material, it always has a lower value than the tensile strength. Elongation shows a significant difference by material, ranging from approximately 14% to 75%. For example, a combination with a tensile strength of 100 KSI, 689 MPa, and a yield strength of 70 KSI, 485 MPa, corresponds to a high-strength material. Overall, the data shows a trend where as strength increases, elongation or ductility tends to decrease.
Finally, let's interpret the modulus of elasticity and the footnotes below the table. The modulus of elasticity ranges from 14 times 10 to the power of 6 psi, or 9.7 times 10 to the power of 4 MPa, to 31.4 times 10 to the power of 6 psi, or 21.7 times 10 to the power of 4 MPa. Stainless and carbon steel series tend to have high stiffness, roughly 28 to 31 times 10 to the power of 6 psi, while cast iron series are relatively lower, around 9.9 to 15 times 10 to the power of 6 psi. The footnotes below the table are also important. Number 1 refers to materials tempered at 1,200 degrees Fahrenheit, 650 degrees Celsius. Number 2 refers to annealing, and number 5 refers to rot condition. Additionally, numbers 3 and 4 specify that the tests were conducted using A126 Class B and Class C materials with a 1.125 inches, 95 millimeters, diameter bar, respectively.
I would like to introduce the modulus of elasticity, which is one of the items in the valve material properties table. This value is measured based on 70 degrees Fahrenheit, or 21 degrees Celsius, and is expressed in psi with the MPa value provided in parentheses. The modulus of elasticity is a measure of stiffness, indicating how well a material resists deformation when subjected to a load. When evaluating materials used for the pressure-containing parts of a valve, this modulus of elasticity is considered along with tensile strength, yield strength, and elongation. The reason for setting the reference temperature at 70 degrees Fahrenheit is to standardize the properties at room temperature so that different materials can be compared under the same conditions.
The modulus of elasticity section continues. Since the material properties table for pressure-containing parts is extensive, it is divided across several pages, and the modulus of elasticity column based on 70 degrees Fahrenheit is repeated in the same format each time. Similarly, the units are written in psi with MPa in parentheses. Using it is simple. find the material code row on the left side of the table, then read the modulus of elasticity value in the same row. Even if the table is split into several pieces, the definition of the column remains the same, so it can be used as a consistent standard when comparing the stiffness of different materials.
This chunk contains hardness-related properties of valve materials and a transition to the next topic. Representative Brinell hardness items include cases where 60 to 80 HRB is required, and 37 HRC is also presented. Additionally, a typical hardness value of 93 with 638 in parentheses is listed along with a reduction of area of approximately 17%, and the modulus of elasticity is shown at the level of 30 million psi, or 210,000 MPa. HRB and HRC refer to the B scale and C scale of Rockwell hardness, respectively. At this point, the material properties table for pressure-containing parts concludes, and the physical constants table for hydrocarbons begins. This table will cover data such as molecular weight and boiling point for each compound.
Next, we turn to fluid properties.
I would like to introduce the boiling point, which is a key column in the physical constants table for hydrocarbons. This column shows the boiling point in degrees Fahrenheit based on an absolute pressure of 14.696 SI. 14.696 SI is the absolute pressure equivalent of 1 atmosphere, which is the standard atmospheric pressure, commonly referring to ambient pressure conditions. The table summarizes the boiling points of each hydrocarbon compound under these conditions, and the No. column serves as an identification number for the compounds. It is important here that the unit is SI, meaning absolute pressure. This should not be confused with gauge pressure, and these boiling point values are used as reference data when calculating phase changes or vapor pressure.
I will now introduce the molecular formula, molecular weight, and boiling point data for hydrocarbon compounds. The lightest, methane, has the molecular formula CH4, a molecular weight of 16.043, and a boiling point of minus 258.69 degrees Fahrenheit. Ethane is C2H6, 30.070, with a boiling point of minus 127.48 degrees Fahrenheit, and propane is C3H8, 44.097, with a boiling point of minus 43.67 degrees Fahrenheit. Butane has the molecular formula C4H10 and the same molecular weight of 58.12, but the boiling points differ by structure. N-butane is 31.10 degrees Fahrenheit, and isobutane is 10.90 degrees Fahrenheit. Pentane isomers all have the formula C5H12 and a molecular weight of 72.151, but their boiling points vary. N-pentane is 96.92 degrees Fahrenheit. Isopentane is 82.21 degrees Fahrenheit. And neopentane is 49.10 degrees Fahrenheit. Hexane is C6H14 with a molecular weight of 86.178, where N-hexane is 155.72 degrees Fahrenheit and neohexane is 121.52 degrees Fahrenheit. Heptane is C7H16 with a molecular weight of 100.205, where N-heptane is 209.17 degrees Fahrenheit and 2,2-dimethylpentane is 174.54 degrees Fahrenheit. The key point is that isomers with the same number of carbons have the same molecular weight, but the boiling point changes depending on the branch structure.
I would like to introduce the column structure leading to the freezing point and vapor pressure in the hydrocarbon physical constants table. Like the boiling point mentioned earlier, this column is also based on an absolute atmospheric pressure of 14.696 SI. The additional item is the freezing point, with units in degrees Fahrenheit. Following the freezing point is the vapor column, which refers to vapor pressure. Since the boiling point, freezing point, and vapor pressure are all arranged side by side based on the same pressure reference, you can look up the phase change temperature and vapor pressure of a specific hydrocarbon all at once in a single table.
Now, I will introduce the column configuration for organizing critical properties and specific gravity data in the hydrocarbon properties table. This table presents the properties of each hydrocarbon compound across several columns. First is the vapor pressure, expressed in SI at 100 degrees Fahrenheit. Next is the gas-specific gravity, which is a relative value compared to air as 1.0 at 60 degrees Fahrenheit, and this reference is specified in Note 1. Then, the critical temperature is given in degrees Fahrenheit, and the critical pressure is given in psi. Finally, the liquid-specific gravity is expressed under the 60 degrees Fahrenheit per 60 degrees Fahrenheit condition according to the criteria in Notes 3 and 4. Values enclosed in parentheses in the table, such as 5,000, 800, or 190, represent estimated or reference data.
Here, we cover the critical properties and measured specific gravity values of paraffinic hydrocarbons from methane to heptane. Looking at the critical temperatures, methane is minus 116.63, ethane is 90.09, propane is 206.01, and butane is 305.65, and isobutane is 274.98 degrees Fahrenheit. For critical pressure, methane is 667.8, ethane is 707.8, and propane is 616.3 psi. Generally, it decreases as the number of carbons increases. Gas-specific gravity, with air as 1.0, increases in proportion to molecular weight. Methane is 0.5539, ethane is 1.0382, and propane is 1.5225. N-pentane and isopentane have critical temperatures of 385.7 and 369.1 and critical pressures of 488.6 and 490.4, respectively. The hexane series has a liquid-specific gravity between 0.654 and 0.664, and the gas-specific gravity is identical at 2.9753. The heptane series has critical temperatures ranging from 477 to 513 degrees and a gas-specific gravity of 3.4696. Values marked with Note 5 represent ultra-low temperature freezing points, such as minus 296.46 or minus 305.84.
This part is the column header for the boiling point in the hydrocarbon physical properties table. The boiling point is measured at a reference pressure of 14.696 psi, which is standard atmosphere pressure, and the unit is degrees Fahrenheit. This column is a continuation of the previous hydrocarbon properties table, and it is organized so that the temperature at which each compound begins to boil can be compared under the same reference pressure.
Here, the boiling point column header is repeated. The same header is rewritten as the table moves across pages or blocks. The reference remains 14.696 psi, and the unit is degrees Fahrenheit. Following this header, the boiling point data for the next block of compounds, such as those with 8 or more carbons and the olefin series, will follow.
This section presents the molecular formulas, molecular weights, and boiling points for paraffins with 8 or more carbons, cyclic hydrocarbons, and the olefin series. N-octane, isooctane, and disobutyl all have the molecular formula C8H18 and the same molecular weight of 114.232, but their boiling points differ at 258.22, 210.63, and 228.39 degrees Fahrenheit, respectively. N-nonane is C9H20 with a molecular weight of 128.209 and a boiling point of 303.47, and N-decane is C10H22 with a molecular weight of 142.286 and a boiling point of 345.48. For cyclic hydrocarbons, cyclopentane is C5H10 with a molecular weight of 70.135. Cyclohexane is C6H12 at 84.162. And methylcyclohexane is C7H14 at 98.189. In the olefin series, ethylene is C2H4 with a molecular weight of 28.054 and a boiling point of minus 154.62. And propene is C3H6 at 42.081. The butene isomers all have the same molecular formula C4H8 and molecular weight of 56.108. But the boiling points are distinguished as 1-butene at 20.75, cis-2, butene at 38.69, trans-2, butene at 33.58, and isobutene at 19.59. For the diene series 1,3-butadiene and 2-butadiene are C4H6 at 54.092, and isoprene is C5H8 at 68.119 with a boiling point of 93.3. The gas-specific gravity column also indicates that it is based on air being 1 at 60 degrees Fahrenheit.
I would like to introduce the column configuration of the physical constants of hydrocarbons table. This segment is the header part of the table, distinguishing the freezing point column and the critical constants columns. The freezing point is measured at 14.696 IA, which is standard atmospheric pressure, and the unit is Fahrenheit. Since 14.696 IA is the absolute pressure corresponding to 1 atmosphere, it allows the state properties of all compounds to be aligned and compared at the same reference pressure. The critical constants group encompasses the critical temperature and critical pressure columns that follow, and this header serves to define the position of the freezing point and critical values for each data row.
Following the previous slide, I will introduce the part where the freezing point column and the vapor pressure column are connected. The freezing point is expressed in Fahrenheit based on 14.696 IA, and the next header moves to the vapor pressure or vapor column. Unlike the freezing point, vapor pressure is expressed at a separate reference temperature of 100 degrees Fahrenheit. By following this sequence from freezing point to vapor pressure, you can sequentially understand the liquid and gas behavior of each hydrocarbon. Since the freezing point shares the same reference pressure of 14.696 IA, it is used to directly compare phase change temperatures between compounds.
I will now introduce the vapor pressure column. This header is for the vapor pressure column, with a measurement reference of 100 degrees Fahrenheit and the unit in SIA, which is absolute pressure. 100 degrees Fahrenheit corresponds to approximately 37.8 degrees Celsius, and it represents the saturated vapor pressure at this temperature. Since SIA is absolute pressure with zero set at a vacuum, care must be taken not to confuse it with gauge pressure. Because vapor pressure is a key indicator of how easily each hydrocarbon vaporizes, it is the first column looked at when comparing volatility and vaporization tendencies between compounds.
I will introduce the first set of hydrocarbon critical constants and specific gravity data. The vapor pressure at 100 degrees Fahrenheit is listed across a wide range, from 0.537 to 9.914 SIA. The critical temperature column contains values in Fahrenheit, such as minus 70.18, minus 132.07, minus 161.27, and 226.4. Critical pressure is noted as 564.22, 530.44, 729.8, and 669 SIA. The liquid-specific gravity, based on 60 degrees Fahrenheit, ranges from 0.7068 to 0.7834. According to the notes, values like minus 272.45 refer to the triple point, or the value at saturation pressure. Numbers in parentheses are estimated values, and note 7 indicates the reference is the saturation pressure at 60 degrees Fahrenheit.